In this exercise, we have two cylinders that intersect at 60 degrees. The diameters are 4 and 2 meters respectively. We are to find the arc length of the curve of intersection between the two cylinders. The curve of intersection between the two cylinders is made up of two closed curves, neither of which is a planar curve. If the curve of intersection is given by the vector function r of t with components x of t, y of t, and z of t with t between a and b, assuming that r is differentiable, then the arc length of r is the integral from a to b of the magnitude of r prime of t, so that the integrand is the square root of the sum of the squares of the derivatives of x, y, and z with respect to t. To find a formulation for r of t, we first find equations for the two cylinders. Let C sub 1 be the big cylinder. Designate the y-axis to be the central axis of C sub 1. Since the diameter of C sub 1 is 4 meters, an equation for C sub 1 is x squared plus z squared equals 4. Finding an equation for the small cylinder is not quite as straightforward. To find an equation for the small cylinder, we start with the cylinder which we call C sub 2, and whose equation is x squared plus z squared equals 1. C sub 2 has the same radius of 1 meter as the small cylinder in the exercise. The one big difference is that this cylinder, like the big cylinder, has the y-axis as its central axis, so that it is parallel to cylinder C sub 1 and does not intersect C sub 1 at 60 degrees. Let C sub 3 be the small cylinder in the problem. We obtain an equation for small cylinder C sub 3 in the problem by rotating cylinder C sub 2 with the z-axis as the axis of rotation. To the equation for C sub 2, we apply the rotation transformation where x is replaced by x times cosine 60 degrees minus y times sine 60 degrees, or by x over 2 minus y times the square root of 3 divided by 2. In the same rotation transformation, we replace y by x times sine 60 degrees plus y times cosine 60 degrees, or by x times the square root of 3 divided by 2 plus y over 2. This rotation transformation effects the rotation we require so that cylinder C sub 2 is rotated onto cylinder C sub 3. We can verify this by examining how the rotation transformation affects the y-axis, which is the central axis of C sub 2, and how it affects the intersection curves between C sub 2 and the xy plane. The equation of the y-axis on the xy plane is x equals 0. Under the rotation transformation, where we replace x by x over 2 minus y times the square root of 3 divided by 2, the equation x equals 0 becomes x over 2 minus y times the square root of 3 divided by 2 equals 0. The traces of C sub 2 on the xy plane, or the intersection curves between C sub 2 and the xy plane where z equals 0, are the lines x equals minus 1 and x equals 1. Applying the rotation transformation to these equations, we get the following equations. X over 2 minus y times the square root of 3 divided by 2 equals minus 1, and x over 2 minus y times the square root of 3 divided by 2 equals 1. These lines are mutually parallel. Their slopes are all equal to 1 divided by the square root of 3, which is tangent 30 degrees. So that each of these lines forms an angle of 30 degrees with the positive x-axis. And so each of these lines, which are all vertical on the xy plane, is rotated clockwise 60 degrees around the origin. And so the rotation transformation indeed rotates C sub 2 onto C sub 3. We apply the rotation transformation to C sub 2 to get the equation for C sub 3. We get the equation, the square of the quantity x over 2 minus y times the square root of 3 divided by 2 plus z squared equals 1. Z goes from minus 1 at the bottom of C sub 3 to z equals 1 atop cylinder C sub 3. Having the bounds for z makes it seem like z would be a natural choice for the parameter for the parameterization for the intersection curve between the two cylinders. So we let z be the parameter t, with t between -1 and 1. We proceed to solve for x and y in terms of t. From the equation of c sub 1, we find that x equals plus or minus the square root of 4 minus z squared, or plus or minus the square root of 4 minus t squared. We use the equation for c sub 3 to solve for y. Y should be equal to the quantity x over 2 plus or minus the square root of 1 minus z squared, the whole quantity multiplied by 2 divided by the square root of 3. If we take x to be square root of 4 minus t squared so that x is positive, y should be equal to the quantity the square root of 4 minus t squared divided by 2 plus or minus the square root of 1 minus t squared and the entire quantity multiplied by 2 divided by the square root of 3. We have also replaced z by t to get this last equation. For negative values of x, with x equals minus the square root of 4 minus t squared, y equals the quantity minus the square root of 4 minus t squared divided by 2 plus or minus the square root of 1 minus t squared, the entire quantity multiplied by 2 divided by the square root of 3. We are just about ready to set up the integral for the arc length of the intersection between the two cylinders. But first, we examine how the curve is traced by the parameterization or parameterizations as t increases from t equals -1 to t equals 1. This should give us a better idea on how to set up the integral or integrals for the arc length of the intersection between the two cylinders. We will use the small cylinder as a point of reference. Let us first examine the portion of the curve when x equals the square root of 4 minus t squared, or when x is positive. This portion of the curve of intersection has two pieces because of the term plus or minus the square root of 1 minus t squared in the formulation of y. For the first piece, we use plus the square root of 1 minus t squared. This piece starts at point A at the bottom of the cylinder where z equals t equals -1. As t increases, the curve crosses the xy plane at the point B where t equals z equals 0, and continues to the point C when t equals z equals 1 atop the small cylinder. If instead we use minus the square root of 1 minus t squared in the formulation of y, the second piece still starts at the point A, but continues on the other side of the cylinder where it intersects the x-axis, and continues on to the point C. And so we have one of the loops of the intersection between the two cylinders. The second loop corresponds to the values of x that are negative, or when x equals minus the square root of 4 minus t squared. Then, y equals the quantity minus the square root of 4 minus t squared divided by 2 plus or minus the square root of 1 minus t squared, this entire quantity multiplied by 2 divided by the square root of 3. If we take plus the square root of 1 minus t squared in the parameterization for y, the curve starts at the point E at the bottom of C3 where t equals z equals -1. The curve proceeds to intersect the x-axis when t equals z equals 0 at the point F, and continues to the point G where t equals z equals 1. If instead we take minus the square root of 1 minus t squared in the formulation of y, just as in the first loop, this portion lies on the other side of the cylinder. Each loop is a mirror image of the other loop because the parameterizations of x and y in one loop are just the negatives of the parameterizations of x and y in the other loop, so that the loops together form a curve that is symmetric with respect to the z-axis. We set up the arc length integral or integrals for the loop where x is greater than 0 or when x equals the square root of 4 minus t squared. Then multiply the result by 2 to get the total arc length of the curve of intersection. Let the vector function r sub 1 be for the portion when x is greater than 0 or when x equals the square root of 4 minus t squared. We use plus the square root of 1 minus t squared in the formulation for y, so that y equals the quantity the square root of 1 minus t squared plus the square root of 4 minus t squared divided by 2 with the entire quantity multiplied by 2 and then divided by the square root of 3. Z is still equal to t. The viewer can check that r sub 1 prime of t is given by this vector function. So the arc length of r sub 1 is equal to the integral from minus 1 to 1 of the magnitude of r sub 1 prime. In other words, the integrand is equal to the square root of the sum of the squares of the components of r sub 1 prime. Calculating this integral numerically up to 5 significant digits, the arc length of r sub 1 equals 3.6640 meters. Now let r sub 2 be the rest of the loop where x is positive. This time we take minus the square root of 1 minus t squared in the parameterization for y. And so the arc length of r sub 2 should be equal to the integral from minus 1 to 1 of the magnitude of r sub 2 prime. Calculating this integral numerically, we find that the arc length of r sub 2 up to 5 significant digits is 3.2329 meters. The arc length of one loop is equal to the sum of the arc lengths of r sub 1 and r sub 2. Therefore, the arc length of one loop is equal to 6.8969 meters. And multiplying by 2, the total arc length of the intersection between the two cylinders up to 5 significant digits is 13.794 meters.